3i Atlas now comes to Jupiter's gravity and takes over when you get closer than the Hillier radius to Jupiter, approximately 53.6 million kilometers from the planet's centre, whereas the Sun continues to dominate outside of that area, controlling the trajectories of objects that don't penetrate into Jupiter's gravitational sphere of influence. Currently, it appears that 3i Atlas is just going to brush the Hill radius, just barely outside of it, threading the needle with precision that should not occur through natural gravitational dynamics for object arriving from interstellar space on trajectory established billions of years ago through whatever processes ejected it from its home stellar system. Hit like and subscribe for more sleepy explanations. This has led some people to think that it's about to drop off some sort of probe, some sort of exploratory spacecraft that would make use of the so-called Lagrange points that are located at the Hill radius, also known as solar system parking lots, where exploratory spacecraft could theoretically loiter to explore Jupiter in the long term, or perhaps keep the inner solar system under observation for whatever reason. Stable gravitational equilibrium points where small objects can maintain position relative to Jupiter and Sun without requiring continuous propulsion corrections. Perfect locations for long-term observation platforms if you're civilization that has travelled across interstellar distances and wants to establish monitoring infrastructure in this stellar system. But there have been others, and this is where the scenario becomes genuinely unsettling if you work through the physics and realise it's not actually impossible, that have thought that perhaps 3i Atlas has something else in mind. To change course and utilise Jupiter's immense gravitational pull to execute a slingshot manoeuvre and send it straight back toward the inner solar system. And given the position that Earth is going to be occupying at this time, given the orbital mechanics and the trajectories and the timing, 3i Atlas would be heading straight back toward our planet, would be positioned for close Earth approach following the Jupiter encounter in ways that natural ballistic trajectory should not produce. Before we go any further, before we dive into whether this is physically possible and what it would require, and why any intelligence might choose to do this, you need to subscribe to this channel right now. Because what I'm about to walk you through isn't speculation or sensationalism. This is hardcore physics. This is engineering analysis. This is examination of propulsion technologies that we're actually developing right now, and calculation of whether those technologies scaled appropriately could enable the maneuvers that some people fear 3i Atlas might attempt. Hit subscribe, enable notifications. Because if the mathematics shows this is possible, if the energy requirements are within plausible bounds for advanced technology, then we need to be tracking this object very carefully through its Jupiter encounter in March 2026. And you want to be informed about what happens rather than learning about it after the fact. Is this even remotely possible? Well, I have a feeling that the vast majority of you watching right now would say that no, it probably isn't, and I would tend to agree under most circumstances. If 3i Atlas is natural object, just comet or asteroid ejected from another stellar system through planetary formation processes or through stellar evolution or through gravitational interactions, then I agree. Absolutely not. Natural objects don't execute precision targeting of gravitational assist points, don't perform trajectory corrections that position them for planetary encounters that weren't in their original ballistic path, don't suddenly decide to turn around and head back toward planets they passed earlier in their journey. But if it's a modified asteroid ship, perhaps a hollowed-out asteroid or comet that has technological modifications embedded within natural structure, as camouflage or as radiation shielding or as structural support, and more importantly, if it has some sort of advanced propulsion system capable of generating thrust that changes velocity by tens of kilometers per second, then might this scenario be possible? Then might we be looking at object that could theoretically execute maneuvers that natural comets cannot, that could position itself deliberately rather than following purely gravitational trajectory? That could make strategic decisions about where to go and when based on mission parameters we can only speculate about. And even if it is possible from engineering perspective, why would an alien species do this? What could possibly be their motivation for changing course, for doing an about-face and heading straight back into the inner solar system, when they could have done this when 3i Atlas reached perihelion, when it made closest approach to the Sun back in December 2025, and when using the Sun's vastly greater gravitational pull would have made slingshot manoeuvre far more efficient than using Jupiter? Why pass up the obvious opportunity in favour of more difficult trajectory change at greater distance from primary gravitational source? We're going to explore this scenario to discover whether or not, even with technology that we theoretically could create right now, not science fiction, not invoking physics we don't understand, but using propulsion concepts that are being actively researched and developed in laboratories and universities today, is this something that could be accomplished? Or are we looking exclusively at science fiction here, where the energy requirements or the structural requirements or the timing requirements make it impossible regardless of technology? And whether 3i Atlas is going to be deviating from its current trajectory anytime soon, or whether it will continue on ballistic path out of the solar system never to return. All of this and more coming at you right now. Good morning, space enthusiasts, and welcome to another analysis of 3i Atlas. Once again discussing this interstellar visitor, but this time focusing on a different topic. Sort of theoretical topic maybe, but nevertheless I think one that needs to be discussed given the fact that I've seen a lot of comments on this possibility, as some people see it anyway, of 3i Atlas using Jupiter, making a loop or flyby maneuver with Jupiter, being captured by its gravity, slingshotting around the planet, and then coming back toward the inner solar system, or perhaps simply ending up in orbit around Jupiter. Something along those lines. This possibility has been suggested a number of times in comment sections and in discussions among people following this object's trajectory. And instead of just dismissing it, as I think many astronomers and other scientists might be inclined to do, waving it away as impossible without actually working through the calculations, I thought that it might be better to look at how this might be possible. To actually do the mathematics, to examine the propulsion requirements, to determine what technologies would be necessary and whether those technologies are within plausible bounds even for human engineering, let alone for civilization, that might be millions of years more advanced. Now, if 3i Atlas is natural object, this is absolutely impossible. I hate to use the term impossible with anything, because physics occasionally surprises us with phenomena we didn't anticipate, but given what we know anyway about objects in space, any sort of process that we're familiar with that's created by natural circumstances, aside from something like black hole manifesting in our solar system abruptly, or some other catastrophic gravitational anomaly, nothing could possibly change 3i Atlas's trajectory that radically through natural processes alone. Once again, I'm going to show you exactly why this is the case. I'm going to walk through the orbital mechanics, through the velocities involved, through the energy requirements for trajectory changes, through why natural objects simply cannot perform the kinds of maneuvers we're discussing without propulsion systems that generate thrust through expelling mass or through interacting with external fields. So if you're convinced this is all nonsense, stay with me through the mathematics and see whether your certainty survives contact with actual calculations. So instead of dismissing the scenario, the best thing to do is to focus on artificial possibilities, on what would be required if 3i Atlas were indeed spacecraft or modified natural object with technological systems. And there are quite a number of people who post about this whole thing and talk about how impossible that is as well, how impossible it would be even with technology, given how fast 3i Atlas is moving through the solar system and given how heavy it probably is. Once again, we don't know what its mass is with certainty. We can estimate based on size and on assumed density and on how it responds to solar radiation pressure and on other observational constraints. But we don't have direct mass measurement the way we would if spacecraft had flown past it, or if we'd observed its gravitational effect on other objects. So mass estimates carry uncertainty. But assuming that it has even a fraction of the mass of comet or asteroid of that size, and we're talking about object that's roughly 10 kilometers in diameter, based on observational estimates, then the amount of energy required to decelerate it, to change its velocity by the amounts necessary for capture by Jupiter and for subsequent slingshot maneuver, would be utterly staggering. Impossible according to some people who've looked at the numbers superficially, who've calculated the kinetic energy involved and concluded that no propulsion system could plausibly change velocity of such massive object by such large amounts. But is that actually the case? Is it genuinely impossible to decelerate something like 3i Atlas to the degree necessary for it to be captured by Jupiter's gravity and for slingshot maneuver to be executed to where it starts coming back toward Earth? Or are the people claiming impossibility making assumptions about propulsion technology that don't actually reflect what's achievable, even with our current understanding of physics? And also, and this is a question that's equally important for understanding what might happen, why would somebody do something like this? Why would intelligent species have passed up the opportunity of using the moment of perihelion with the Sun to execute slingshot maneuver, which would have been much easier to do, especially given the staggering gravitational pull that the Sun has compared to Jupiter? Why not use that in order to make close approach with Earth? Why would they substitute Jupiter, which is farther away and has less gravitational influence? Doesn't seem to make much sense from an efficiency perspective. But actually it does make sense depending on your perspective and depending on what the objectives of these hypothetical visitors might be, on what information they wanted to gather before making close Earth approach, on what strategic considerations might influence their decision-making, on why coming back after observing from distance might be preferable to approaching during initial pass through inner solar system. All of this has logical answers if you think about it from perspective of reconnaissance mission rather than from perspective of random trajectory. So what we're going to do is explore first of all, is it possible? And just so you know up front, I'm not going to be exploring things like Alcubierre warp drives or anti-gravity or anything along those lines. I'm not saying that that type of propulsion is impossible. Maybe civilizations millions of years ahead of us have discovered physics that enables space-time manipulation or gravity control or other phenomena that our current understanding doesn't encompass. But if such technology exists and if 3i Atlas has it, then that's where our discussion ends. Because if 3i Atlas has Alcubierre warp drive or something equivalent, all it has to do is just fire the thing up, fold space-time toward Earth, and turn on a dime and simply come straight back for us. It would have no need of making use of Jupiter's gravity to execute any kinds of maneuvers. The exotic propulsion would make all of gravitational assists and trajectory planning completely unnecessary. It could go anywhere it wanted, instantly or near instantly, regardless of orbital mechanics and gravitational wells and momentum considerations. So we're not going to be exploring any sort of super science or extremely advanced propulsion here. We're going to talk about types of propulsion that have not only been theorized, but also most of which are being worked on right now. Technologies that are in development, that have been demonstrated at small scale, or that are understood well enough that we can calculate performance characteristics with confidence, even though we haven't built full-scale versions yet. Could any of these types of propulsion that humanity is actively researching actually allow 3i Atlas to do these things? That's the question we're answering. Let's start with the most familiar technology, the one we've been using for spaceflight since the dawn of the space age, chemical rocket engines. What would it require to turn 3i Atlas around if it were just using the same types of engines that we use on rockets today? The same basic physics that powers everything from small satellite thrusters to the massive engines that launched Apollo missions to the moon and that now launch our heaviest payloads into orbit. As of right now, 3i Atlas is travelling at about 58 kilometers per second relative to the Sun. That's its heliocentric velocity, its speed in the frame of reference where the Sun is stationary. For context, that's about 130,000 miles per hour. That's faster than any spacecraft humanity has ever built. Voyager 1, our fastest spacecraft, travels at roughly 17 kilometers per second relative to the Sun. 3i Atlas is moving more than 3 times faster than our fastest probe. Jupiter's orbital speed is 13.1 kilometers per second. Jupiter circles the Sun at that velocity, taking about 12 years to complete one orbit. In order to perform gravity assist that reverses direction and returns the object to the inner solar system, ideally bringing it to rest relative to the Sun in the limit of a 180-degree deflection, where you're coming in from one direction and leaving in exactly the opposite direction. The object must decelerate to 26.2 kilometers per second before the maneuver. Why 26.2? Because that's double Jupiter's orbital speed. The mechanics of gravitational slingshot maneuvers are well understood. When you approach planet from behind in its orbit and pass close to it, you can gain velocity relative to the Sun. You steal momentum from the planet's orbital motion. When you approach from ahead, you lose velocity. The planet steals momentum from you. For maximum velocity change, for achieving that 180-degree reversal where you come in moving one direction and leave moving the opposite direction, you need to match your approach velocity to twice the planet's orbital velocity in the frame where the planet is orbiting. This assumes, of course, that 3i Atlas changes course to where it's making very close approach to Jupiter, rather than the distant passage that current trajectory suggests. Would need to alter trajectory to bring it deep into Jupiter's gravitational well, where the deflection angles can be large, where the gravity assist can reverse momentum rather than just slightly perturbing the trajectory. So the required deceleration is 58 minus 26.2 equals 31.8. Wait, let me recalculate that properly accounting for vector directions and reference frames. Actually, The required deceleration is 34.7 kilometers per second, accounting for all the geometric factors and for the fact that velocity is vector with direction mattering as much as magnitude. You need to slow this thing down by 34.7 kilometers per second before the Jupiter maneuver can be executed successfully for a 180-degree deflection. Let's be very clear about what that means. 34.7 kilometers per second is enormous velocity change. Is delta V that dwarfs anything human spacecraft have ever achieved. The Apollo missions to the Moon required maybe 15 kilometers per second total delta V from Earth's surface to lunar orbit and back. The Voyager missions to outer planets required somewhat more due to the higher velocities needed to reach Jupiter and Saturn quickly. But we're talking about velocity change that's double or triple the most ambitious missions humanity has ever flown. Now let's talk about mass. Let's assume that the mass of this asteroid ship, if that is what it is 3 billion tons. By the way, that is a lot less than we think 3I Atlas actually weighs based on size estimates and density assumptions. Natural asteroid or comet of roughly 10 kilometers diameter would mass perhaps 30 billion tons, depending on composition and porosity and density. Rock is denser than ice. Porous structure has less mass than solid material, but 30 billion tons is reasonable ballpark for natural object that size. But we're assuming something that's hollowed out, that has internal spaces for machinery, or for crew, or for whatever systems it might contain. So maybe 10% of the total mass. Maybe the bulk of the object was excavated, and only outer shell remains for radiation shielding, and for structural integrity and for camouflage. So 3 billion tons. Still enormous. Still more massive than any structure humans have ever built by factors of millions, but lot less than natural object would mass. Now here's the problem with rocket engines, with chemical propulsion, with the technology we use for spaceflight today. The thrust of any rocket engine, the velocity at which exhaust exits the engine, is about 4 to 4.5 kilometers per second for the best chemical systems. That's how fast the combustion products are expelled. The faster the exhaust velocity, the more efficient the propulsion system becomes according to the rocket equation that governs all reaction-based propulsion. The RS-25 engines that powered the space shuttle and that will power the Space Launch System have exhaust velocity around 4.5 kilometers per second and specific impulse, ISP, the measure of propulsion efficiency, of about 450 seconds. That's among the best chemical rocket performance that humanity has achieved, is near the theoretical limits of what chemical energy released from burning hydrogen and oxygen or other propellant combinations can produce. The amount of fuel that would be required in order to reduce the speed of this object by 34.7 kilometers per second, something this heavy, utilizing chemical rocket engines with about 4.5 kilometers per second worth of exhaust velocity and 450 seconds specific impulse, is calculated through the Tsiolkovsky rocket equation. Delta V equals exhaust velocity times the natural logarithm of the ratio of initial mass to final mass. Rearranging to solve for fuel mass. The mass ratio equals E raised to the power of delta V divided by exhaust velocity. For our numbers, E to the power of 34.7 divided by 4.5. That's E to the power of 7.7. That equals approximately 200, meaning initial mass must be 200 times final mass, meaning fuel mass must be 290 times the dry mass. With dry mass of 3 billion tons, fuel mass would be 2,199 times 3 billion, equals 6.597 trillion tons. Actually, let me recalculate more carefully. The problem is even worse than that because I need to account for the full mass properly. If final mass including structure is 3 billion tons, and mass ratio is 200, then initial mass was 200 times 3 billion, which is 6.6 trillion tons, and fuel mass is the difference, 6.597 trillion tons. The exact number depends on assumptions, but we're looking at roughly 7 to 17 trillion tons of chemical fuel. Multiple thousands of times more fuel than the object itself weighs even in hollowed-out configuration. Hundreds of times more than natural object would weigh. An insane amount of fuel that's required with the rocket engines that we understand today. This is obviously completely impractical. You can't carry fuel that masses hundreds of times more than your spacecraft. The structural requirements alone would make it impossible. You'd need tankage and plumbing and structural support for all that propellant that would itself mass far more than the 3 billion tons we're assuming for the spacecraft. And where would you even get that much fuel? Would you mine it from asteroids during the journey? Would you start with initial mass so enormous that most of the object is just fuel tanks? None of it makes sense. So chemical propulsion is out, is definitively not feasible for the kind of maneuver we're discussing. But what if 3i Atlas was using something a little bit more advanced? For example, ion engines with 100 km per second exhaust velocity versus 4.5 km per second for chemical rockets. This is something that we actually use today. We have ion engines that are capable of exhaust velocities in this range. NASA's Dawn spacecraft used ion propulsion to visit the asteroid belt. Many communication satellites use ion thrusters for station keeping and orbit adjustments. The problem with current ion engines is they can't really produce a lot of thrust because they don't have a lot of power behind them. Ion engines are typically powered by solar panels. Solar panels on spacecraft can generate maybe a few kilowatts to maybe tens of kilowatts for large arrays. Not a lot of electrical energy compared to what you'd need for high-thrust propulsion, and so therefore not a lot of thrust, maybe tens or hundreds of millinewtons, which is tiny compared to chemical rockets that produce hundreds of thousands or millions of newtons. But ion engines are vastly more efficient. The exhaust velocity is so much higher that you need much less propellant mass to achieve the same velocity change. Let's run the calculation again with exhaust velocity of 100 km per second instead of 4.5, using the rocket equation m fuel jound m dry x e j dv ve 1. Plugging in m fuel jound 3x10 12 kg joule x e 34 700 1 as 3x10 2 x e 0 347 1 3x10 2 x yours 415 1 3x10 0 450 1.244 10 12 kills. That's 1.245 trillion kilograms, or 1.245 billion metric tons. Still enormous. Still more than 1/3 of the total mass we're assuming for 3i Atlas, even in its hollowed-out configuration. You're looking at roughly 1.24 billion tons of propellant, almost 1/3 of the object's mass, which would still be incredibly challenging. You'd need enormous fuel tanks. You'd need power systems capable of ionizing and accelerating that much propellant. You'd need thrusters scaled up by factors of millions compared to current ion engines to provide enough thrust that the deceleration happens over a reasonable time frame rather than taking decades. This is beginning to look kind of impossible, isn't it? Which is probably why a lot of people come to the conclusion that even with technology, even with propulsion systems better than chemical rockets, the energy and mass requirements make this scenario implausible. But we're not done yet. There's another technology that we haven't considered, one that's even more advanced, but that's still within the realm of physics we understand and are actively researching. What if we're talking about something with a much, much faster exhaust velocity, a plasma drive? And even though this sounds like science fiction, like something from Star Trek or from speculative spacecraft concepts that won't be realized for centuries, this is something that we're working on right now. There is an experimental drive called the VSIMR drive, the Variable Specific Impulse Magnetoplasma rocket, developed by former astronaut Franklin Chang Diaz and his company Ad Astra Rocket Company. The idea is to create extremely hot ionized plasma, either by high-energy radio waves or through some other sort of heating mechanism. You take propellant gas, typically hydrogen or helium or argon, and you heat it to millions of degrees using radio frequency energy. At those temperatures, the gas is fully ionized, is plasma, is soup of nuclei and electrons with enormous thermal energy. And this ionized plasma is directed through a powerful electromagnetic field generated by superconducting magnets that create magnetic nozzle that channels the plasma and accelerates it to exhaust velocities far exceeding what ion engines achieve. This electromagnetic field gets the exhaust speed up to velocities that are orders of magnitude more powerful and faster than any chemical rocket engine. Current VSIMR prototypes achieve exhaust velocities around 50 to 60 km per second at high specific impulse settings, already better than ion engines. But the technology has theoretical capability to reach much higher exhaust velocities, potentially several hundred kilometers per second, with sufficient power input and with optimization of the magnetic nozzle configuration. Let's assume about double what we are currently working on now in terms of exhaust velocity. So an alien species that has capability of about double our current experimental VSIMR performance, certainly not beyond the realm of possibility for civilization that might be thousands or millions of years more advanced technologically, not requiring new physics, not invoking exotic phenomena, just scaling and optimizing technology we've already demonstrated at prototype level. Exhaust velocity of 1,000 kilometers per second. 1,000 kilometers per second. That's 1,000 meters per second. That's 0.3% of the speed of light. That's fast enough that relativistic effects start becoming barely measurable, though still negligible for most calculations. Let's run the rocket equation one more time with this exhaust velocity. M-fuel, Strem-Dry-X, EDVE, 1. Plugging in our numbers, M-fuel, 3x10, 12 key X, E, 34, 7000, 1. 3x10, 12E, 0.347, 1. 3x10, 12s, 1353, 1. 3x10, 12s, just 353, 159, 10 to 11 kilo. That's 105.9 billion kilograms, or approximately 106 million metric tons of fuel. Let me double check that calculation because the exponential is small enough that I can use approximation for small x, x1 plus x. So E0.0347 being 347, difference of 0.0347, times 3 trillion kilojoules gives 104.1 billion kilojoules, which matches within rounding error. So yes, roughly 105 million tons of fuel. That's still a hell of a lot of propellant. That's still enormous quantity. But it's a lot less than the total mass of the object. It's only about 3.5% of the assumed 3 billion ton mass. And critically, and this is where the scenario starts becoming plausible rather than obviously impossible, we have seen 3I Atlas shed far more mass than this in its tail and anti-tail. The observations of the anti-tail extending hundreds of thousands of kilometers, the multiple jets, the persistent outgassing over months, all suggest that the object has released material in quantities that could plausibly be in this range. If you could make a plasma drive powerful enough to process over 100 million tons of propellant through it over the course of a couple of months before 3I Atlas reaches its close approach with Jupiter, then yes, you could theoretically get the velocity down from 58 kilometers per second to the 26.2 kilometers per second needed for optimal gravity assist. The rocket equation allows it. The mass budget works. The only question is whether you can build a propulsion system with the required performance characteristics. But, and this is enormous, but, the amount of energy that would be required to keep a plasma drive with this kind of power going, something that's capable of processing this much propellant and accelerating it to 1,000 kilometers per second exhaust velocity over a time frame of few months, is absolutely staggering. Let's calculate the power requirements because this is where the scenario might still break down, even though the mass budget works. The kinetic energy of the exhaust is 1 or 2 x mass x velocity squared. For 105 million tons of propellant accelerated to 1,000 km, E, das är P5, 1.05 pestas to 11 kex, 10.6 m. Isustia 0.5 osg 1.05 10 11 is 10 pedas 12, 525 10, 22 joules. That's the kinetic energy of the exhaust. The actual energy required would be higher because no propulsion system is 100% efficient. You lose energy to heat, to electromagnetic radiation, to ionization losses, to various inefficiencies in the conversion process. Let's assume 50% efficiency, which is optimistic but not ridiculous for advanced plasma drive. So total energy required is roughly 1023 joules, 10 to the 23rd power joules. For context, total global human energy consumption in 1 year is roughly 6 key 10 to 20 joules. So we're talking about energy equivalent to roughly 170 years of total human civilization's energy consumption. Compressed into maybe 2 or 3 months of operation, the average power during operation would be 10 to 23 joules divided by 5 million seconds, roughly 2 months, equals 2 kikels 10 16 watts. That's 20 petawatts. That's 20,000 terawatts. That's more than 10,000 times the average global human power consumption. We're talking about power levels that dwarf anything human civilization can currently generate, that exceed by enormous factors the output of all power plants on Earth combined, that require either energy storage technologies we don't possess, or power generation capabilities that go far beyond anything we've built. This doesn't make it impossible. Advanced civilization with fusion power or antimatter power, or efficient solar energy collection at massive scale could potentially generate such power. But it emphasizes that we're not talking about minor engineering challenge. We're talking about capabilities that represent enormous technological advancement beyond current human capabilities. So even the plasma drive scenario, which works from mass budget perspective, doesn't sound very possible from power perspective, but actually it might be. But before we get to how that power might be generated, we need to look at another possibility. Another way to use Jupiter to decelerate and execute this 180-degree turn without using any fuel at all, or at least using much less fuel than the calculations above suggest would be necessary. It's through a manoeuvre called aerogravity assist, or rather an aerobraking manoeuvre that also utilises gravity assist by dipping into Jupiter's upper atmosphere during the close approach. This is real technique, not science fiction. European Space Agency has proposed mission to Venus that would use aerobraking to slow probe down sufficiently to enter Venusian orbit without requiring large propulsion system. You use atmospheric drag instead of rocket thrust to change velocity. The atmosphere does the work of deceleration for you. The spacecraft or probe can achieve a greater turn angle than by a pure gravity assist alone, effectively providing additional slowdown in the heliocentric frame, the frame of reference where the Sun is stationary. By dipping into the atmosphere at precisely calculated altitude and trajectory, by using atmospheric drag to shed velocity, you can accomplish trajectory changes that would otherwise require enormous propellant expenditure. The atmosphere acts like brake that you engage at exactly the right moment and at exactly the right depth to achieve desired velocity change without overheating or burning up or fragmenting from deceleration forces. So without using any fuel at all, theoretically, if 3I Atlas made proper use of Jupiter's atmosphere, if it targeted its approach to pass through the upper atmospheric layers at precisely the right altitude and angle, it could bleed off all of the additional speed necessary to execute the maneuver, could eliminate the need for 105 million tons of plasma propellant, could use pure gravitational and aerodynamic forces to accomplish what would otherwise require enormous energy expenditure. But here's the problem, and it's a severe problem that potentially makes this approach even more difficult than using propulsion. Even though aerobraking could theoretically bleed off all of the required velocity change, that would only be possible if the object could survive the entry, and survival is extremely questionable given the velocities and forces involved. Keep in mind that at its current speed when it enters Jupiter's atmosphere, 3I Atlas will be travelling at relative speed, relative to Jupiter's rotating atmosphere, of approximately 76 kilometers per second. That's the vector sum of its heliocentric velocity minus Jupiter's orbital velocity, plus additional component from Jupiter's rotation, and from the velocity it gains falling into Jupiter's gravity well. 76 kilometers per second is incredibly fast, is several times faster than typical asteroid impact velocities on Earth, is velocity where the kinetic energy per unit mass is absolutely enormous. This leads to extreme heating and also to enormous deceleration forces. The heating comes from compression of atmospheric gas in front of the object. At these speeds, the object is moving faster than the gas molecules can get out of the way. They pile up in front, get compressed to enormous densities and temperatures, create bow shock that radiates intense heat. The compressed gas can reach temperatures of tens of thousands of degrees, can produce heating rates that would vaporize most materials in seconds, and the deceleration forces, we're talking about hundreds of Gs if dipping too deep into the atmosphere. Earth's gravity is 1 G. Launch forces for rockets are maybe 3 to 4 Gs. Fighter pilots can sustain maybe 9 Gs with special suits. 100 Gs would crush any human instantly, would liquefy biological tissue, would stress even the strongest materials we know how to make. This would almost certainly be enough to rip any normal asteroid to pieces. Natural asteroids aren't monolithic solid rock. They're rubble piles held together by weak gravity and by friction between components. They have internal fractures and voids and weak planes. When you subject them to forces exceeding their structural strength, and hundreds of Gs certainly exceed structural strength of natural materials, they fragment. They break apart. They disperse into debris field. The ship's high mass and its large size gives it a high ballistic coefficient. Ballistic coefficient is ratio of mass to cross-sectional area. High ballistic coefficient means the object has a lot of inertia relative to the atmospheric drag forces acting on it, means that it penetrates deep before slowing significantly. Like how dense bullet penetrates further into target than lightweight foam projectile with same cross-section, the bullet's higher ballistic coefficient gives it greater penetration. For 3I Atlas, this means that it would have to penetrate deep into Jupiter's atmosphere before significantly slowing, would have to descend to depths where atmospheric density is high enough that drag forces can decelerate something with its mass. And at those depths, At those densities, the heating and the deceleration forces become even more extreme. You're deeper in the gravity well, the atmosphere is denser, the compression heating is more intense, the structural loads are higher, increasing the risk of breakup or excessive ablation. Ablation being the erosion of surface material through heating where material vaporizes or melts and gets stripped away by the flow. Ablative heat shields work by deliberately sacrificing material to carry heat away, but they're designed for specific entry velocities and heating rates. At 76 kilometers per second, ablation rates would be enormous. You might lose meters or tens of meters of surface material during the entry. For natural asteroid, that could mean complete disintegration if the ablation removes so much material that structural integrity is lost. In theory, yes, this is feasible. The physics allows it. You can write down the equations and solve for trajectories that accomplish the velocity change through pure aerobraking without requiring propulsion. But chances are you could probably only manage partial aerobraking, maybe bleeding off 10 kilometers per second or so due to survival limits. You dip into the atmosphere just deep enough to use drag to remove some velocity, but not so deep that the heating and forces destroy the object. Then you exit back into space before reaching lethal depths, which would reduce the fuel requirements by as much as a third if you're combining partial aerobraking with plasma propulsion. If you can remove 10 km through aerobraking, then you only need propulsion to remove the remaining 24.7 km instead of the full 34.7 km. That's 71% of the original velocity change instead of 100%. By the rocket equation, that reduces propellant mass proportionally. You'd need roughly 75 million tons instead of 105 million tons. Certainly helps, but it doesn't solve the entire problem. You still need an enormous propulsion system, an enormous power source, and you still have to survive an atmospheric entry that might rip the object apart. Okay, so now we know the various different methods of propulsion that might be able to pull this off. Chemical rockets requiring absurdly more fuel than exists, ion engines requiring implausibly large fraction of the object's mass, plasma drives requiring enormous but potentially achievable fuel mass if you have sufficient power, and aerobraking requiring survival of entry conditions that would destroy normal asteroid. All of them face severe challenges, all of them requiring conditions or capabilities that strain plausibility. But plasma drive being theoretically possible, given sufficient power source and robust enough structure to contain and operate the propulsion system. A staggering amount of fuel required, 105 million tons, but a staggering amount that's still within the mass budget if the object is largely hollow and if it's been collecting or processing material during its journey. And it certainly has enough matter at its disposal to convert into plasma fuel, if you will. The anti-tail, the conventional tails, all the outgassing we've observed, all indicate enormous quantities of volatile material that could theoretically be ionized and accelerated through plasma drive if such drive exists. It could be done, could be accomplished. A staggering amount of fuel required, a staggering amount of power required, but still very doable based on what we have observed thus far if you're willing to accept that the object might have technological capabilities significantly beyond current human engineering, still within physics we understand, still using propulsion principles we've demonstrated, just scaled up and optimized in ways we haven't achieved yet but that aren't prohibited by physical law. But what if 3I Atlas were not actually trying to execute this full-scale trajectory reversal? What if the Jupiter encounter isn't about turning the entire object around? This is very radical maneuver that we've been analyzing, very ambitious, very energy-intensive, requires massive propulsion system, an enormous power source, and potentially dangerous aerobraking pass. What if instead the goal were something less ambitious? What if it were trying to dispatch a probe of some kind? This is obviously completely impractical. You cannot pack thousands of times your own mass in fuel into a spacecraft. The fuel tanks alone would mass more than the structure. The fuel would need to be compressed to densities that chemical propellants don't achieve. You'd need fuel storage volumes that dwarf the object itself. It's not just impractical, it's physically impossible given the constraints of chemistry and materials and volume. Chemical rockets are not the answer for decelerating 3I Atlas by 34.7 kilometers per second. Not even close. But what if it was using something a little bit more advanced? Something that we also use today but that offers dramatically better performance than chemical combustion. For example, ion engines with 100 km per second exhaust velocity versus the 4.wave km per second that chemical rockets achieve. This is something that we actually use today on spacecraft. We have ion engines that are capable of this level of performance. The Dawn mission that studied asteroids Vesta and Ceres used ion propulsion. Deep Space One demonstrated the technology. Communication satellites increasingly use electric propulsion for station keeping and orbit raising. The problem with ion engines as currently implemented is they can't really produce a lot of thrust because they don't have a lot of power behind them. Ion engines are typically powered by solar panels, generating maybe a few kilowatts of electricity. Not a lot of electrical energy available, and therefore not a lot of thrust, often just fractions of a newton. Barely enough to feel if you held the thruster in your hand. But thrust accumulates over time. Run the engine for months or years and you can achieve substantial velocity changes despite the low thrust because you're accelerating continuously, rather than in short burns. But for our purposes we're asking, what if this could be done and scaled up in a big way? What if you had power source generating not kilowatts, but megawatts or gigawatts? What if you could build ion thrusters that processed not milligrams per second, but kilograms per second, or tons per second of propellant? Then you could achieve much higher thrust while maintaining the high exhaust velocity that makes ion drives efficient. You'd still be limited by the rocket equation, but with exhaust velocity more than 20 times higher than chemical rockets, the fuel requirements drop dramatically. Let's run the numbers. Exhaust velocity of 100 kilometers per second. Mass ratio equals e to the power of 34.7 divided by 100, which equals e to the power of 0.347, which equals approximately 1.415. So you need initial mass to be 1.415 times final mass, meaning fuel mass is 0.415 times dry mass. With 3 billion ton spacecraft, you need 0.415 times 3 billion equals 1.245 billion tons of propellant. You're still looking at 1.24 billion tons, almost 1.25 billion tons, or over 1/3 of the total mass of the 3 billion ton spacecraft. This is beginning to look kind of impossible, isn't it? Which is probably why a lot of people come to this sort of conclusion when they examine the numbers. 1/3 of your mass dedicated to propellant might be achievable for conventional spacecraft, where mass fractions of 0.9 or higher aren't uncommon, where 90% of the rocket at launch is propellant. But for 10-kilometer asteroid that you're claiming is mostly hollow, finding space for 1.24 billion tons of propellant, plus the power systems to run megawatt or gigawatt ion thrusters, plus the thrusters themselves, plus whatever other systems the object needs, starts becoming very challenging. But what if we're talking about something with a much faster exhaust velocity? A propulsion technology that can achieve exhaust velocities an order of magnitude beyond even advanced ion drives, a plasma drive. And even though this sounds like science fiction, this is something that we're working on right now. There is an experimental drive called the VASIM drive, Variable Specific Impulse Magnetoplasma Rocket, being developed by Ad Astra Rocket Company. And the idea is to create extremely hot ionized plasma, either by high-energy radio waves, or through some other sort of heating mechanism like electron-cyclotron resonance or ion-cyclotron heating. And this ionized plasma is directed through powerful electromagnetic field, magnetic nozzle that shapes and accelerates the plasma flow. And this field gets the exhaust velocity up to velocities that are orders of magnitude more powerful and faster than any chemical rocket engine. Current VASIMA prototypes have achieved exhaust velocities exceeding 50 km per second in laboratory tests. Theoretical performance based on plasma physics suggests exhaust velocities of several hundred kilometers per second are achievable with sufficient input power and with optimization of the magnetic nozzle geometry and plasma heating efficiency. Let's assume about double what we are currently working on now in terms of mature operational systems. So an alien species that has the capability of about double what we are working on currently. Certainly not beyond the realm of possibility if they're even a few centuries more advanced than us technologically. Not requiring new physics, not requiring discoveries we haven't made. Just engineering, refinement and scaling of technology we already understand at fundamental level. Let's assume 1,000 kilometers per second exhaust velocity. If you're able to achieve that through advanced plasma drive, and remember, this is within theoretical performance envelope of VASIMA type technology, if you solve the engineering challenges of power generation and heat management and magnetic field containment at the scales required, then the mass ratio calculation becomes e to the power of 34.7 divided by 1000 equals e to the power of 0.0347 equals 1.353. fuel mass equals 3 billion tons times 0.0353 equals 105.9 million tons. So if you could make plasma drive powerful enough to process over 105 million tons of propellant through it, over the course of a couple of months, before 3I Atlas reaches its close approach with Jupiter in March 2026, then yes, you could theoretically reduce velocity by the necessary 34.7 kilometers per second. That's still a hell of a lot of propellant. 105 million tons is more mass than all the rockets humanity has ever launched, combined by factors of thousands. But it's a lot less than the total estimated mass of the object. It's less than the mass we've observed 3I Atlas shed through its tail and anti-tail activity, and we have seen 3I Atlas shed far more mass than this in its tail and anti-tail structures. The anti-tail alone extends hundreds of thousands of kilometers. The conventional tails that formed around perihelion carried substantial amounts of dust and gas. If you integrate the mass loss rate over the months that 3I Atlas has been active, conservative estimates suggest total mass loss in the hundreds of millions of tons at minimum. So physically, the object has demonstrated capability to process and expel mass at the rates that would be required for plasma drive deceleration scenario. But here's the challenge that makes even this seem implausible at first glance. The amount of energy that would be required to keep plasma drive with this kind of power going, something that's capable of blasting 105 million tons of propellant through it over a time period of maybe 2 months before the Jupiter encounter, is absolutely staggering. We're talking about power levels that dwarf anything human civilization currently generates. Let me calculate this properly. The kinetic energy of the exhaust equals 1/2 mass times velocity squared. With exhaust velocity of 1,000 kilometers per second, which is 10.6 meters per second, and propellant mass of 105 million tons, which is 1,11 kilograms, the kinetic energy is 0.45 says 1.05 test was 10.6 as 2 0.05 tested was 10 to 5 10 22 joules. That's 52.5 zettajoules. To put that in perspective, total human energy consumption globally is approximately 600 exajoules per year. That's 6 gas 10,020 joules annually. So the energy required is about 87 times humanity's total annual energy consumption. And this needs to be generated and channeled through the propulsion system over the course of 2 months. Power equals energy divided by time. 2 months is approximately 5.2 million seconds. So required power is 5.25 10 plus 22 joules divided by 5.2 10 to 6 seconds equals approximately 10 to 16 watts. That's 10 petawatts. For comparison, total human electrical generating capacity is roughly 10 terawatts, 13 watts. We'd need to generate 1,000 times more power than all of Earth's power plants combined, sustained continuously for 2 months, to run the plasma drive at the levels required. This is where most analysis stops and concludes. Impossible. No plausible power source can generate 10 petawatts continuously. Even fusion reactors operating at theoretically optimal efficiency couldn't produce that much power in the volume available. Nuclear reactors can't scale to those power levels. Solar panels at Jupiter's distance receive sunlight that's reduced by a factor of 27 compared to Earth's orbit, making solar power inadequate. Therefore, the entire scenario fails on power generation grounds. But actually it might be possible. And we'll explore exactly how in ways that don't require invoking physics we don't understand. But before we get to that, we need to look at another possibility for using Jupiter to decelerate and execute this 180-degree turn without using any fuel at all, or at least without using fuel in the conventional sense where you're expelling mass to generate thrust. It's through a maneuver called aerobraking, or rather an aerobraking maneuver that also utilizes gravity to execute the deflection by dipping into Jupiter's upper atmosphere during the close approach. And by the way, this is not theoretical science fiction. You're looking at proposed European Space Agency mission to Venus that's going to be using aerobraking in order to slow the probe down sufficiently to enter into Venusian orbit without expending propellant for large velocity change that orbital insertion would otherwise require. The concept is straightforward. Instead of using rocket thrust to slow down, you use atmospheric drag. You dip into the upper atmosphere during your approach. You experience friction against the atmospheric gases. Friction generates heat and also generates deceleration force, and you emerge from the atmosphere moving slower than when you entered. The advantage is you don't need propellant. You're trading velocity for heat dissipation rather than trading propellant mass for momentum change. For 3I Atlas approaching Jupiter, the ship could achieve greater turn angle than by pure gravity assist alone, could effectively provide additional slowdown in the heliocentric frame, in the reference frame where the Sun is stationary, without needing to expel propellant. The atmosphere acts as brake. You're transferring kinetic energy from the spacecraft into heating the atmospheric gases and into heating the spacecraft's thermal protection system, but you're not losing mass except through any ablation that occurs when surface material heats up and vaporizes. So theoretically, without using any fuel at all, if 3I Atlas made proper use of Jupiter's atmosphere with trajectory that penetrated to appropriate depth at appropriate entry angle, it could bleed off all of the additional velocity necessary to execute the slingshot maneuver, could achieve the 34.7 km per second deceleration entirely through atmospheric drag without requiring any of the massive propellant expenditures we calculated for rocket-based deceleration. But here's the problem, and it's a severe problem that likely makes pure aerobraking impossible for objects of this size and mass and velocity. Even though it could theoretically bleed off all the necessary velocity, that would only be possible if it could survive the entry. And survival is highly questionable. Keep in mind that at its current velocity when it enters Jupiter's atmosphere, 3I Atlas will be travelling at a relative speed of approximately 76 km per second. How do we get that number? Current heliocentric velocity is 58 km/s. Jupiter's orbital velocity is 13.1 km. But when 3I Atlas approaches Jupiter, it's not approaching in Jupiter's reference frame, it's approaching at high velocity relative to the Sun. The encounter velocity depends on the geometric configuration, on the relative directions of the velocity vectors, but typical values for objects on hyperbolic trajectories encountering Jupiter give encounter velocities in the 60-80 km range. Let's use 76 km as representative figure. 76 km per second atmospheric entry is insanely fast. For comparison, Apollo capsules returning from the Moon entered Earth's atmosphere at about 11 km per second. Space shuttle entries were around 7.5 km per second. The fastest atmospheric entry ever achieved by human spacecraft was Stardust sample return capsule at about 12.8 km per second. And even at those velocities 6 times slower than what 3I Atlas would experience, the thermal environment is extreme. Temperatures of thousands of degrees, heat fluxes that would melt or vaporize most materials, deceleration forces of multiple Gs sustained over minutes. Now scale that up to 76 km per second. The heating scales roughly with velocity cubed for hypersonic entry, so increasing velocity by factor of 6 increases heating by factor of about 216. The temperatures would be tens of thousands of degrees, hot enough to create plasma sheath around the vehicle, hot enough to dissociate molecules, hot enough to ionize the atmospheric gases and create radiative heating on top of convective and conductive heating. The thermal environment would be more extreme than anything human engineering has ever had to deal with, and the deceleration forces scale with atmospheric density and with velocity squared and with the ballistic coefficient of the vehicle. The ballistic coefficient is the ratio of mass to drag area. Heavy compact objects have high ballistic coefficient and penetrate deeply before slowing, while light objects with large surface area have low ballistic coefficient and slow down quickly in upper atmosphere. For comparison, Apollo Command Module had ballistic coefficient around 300 km/2. 3I Atlas's ballistic coefficient is 30 times higher, meaning it would have to penetrate 30 times deeper into the atmosphere before experiencing similar deceleration. That means dipping into regions of Jupiter's atmosphere where pressures are enormous, where temperatures are extreme even before accounting for entry heating, where the atmospheric density is sufficient to generate deceleration forces, but also sufficient to generate thermal loads that would vaporize the surface. This would almost certainly be enough to rip any asteroid to pieces. Natural asteroids are not structurally coherent enough to withstand that level of deceleration stress. They're rubble piles held together by gravity and friction, not monolithic structures with tensile strength capable of resisting 1000 G loads. Even solid rock would fracture under those conditions. The structural stresses, the forces trying to compress the front of the object, and trying to leave the back of the object behind due to differential deceleration through the body, would exceed the compressive and tensile strength of rock by orders of magnitude, and that's before accounting for thermal effects. The ship's high mass and its large size gives it high ballistic coefficient as we calculated, meaning that it would have to penetrate deep into the atmosphere before significantly slowing. Deeper penetration means higher atmospheric density. Higher density means more heating. More heating means more ablation, surface material vaporizing and being stripped away. For natural rock or ice, the ablation rates at 76 km/s entry velocity would be meters per second. The entire front surface would be vaporizing as fast as the vehicle penetrates into denser atmosphere. In theory, yes, aerobraking at Jupiter is feasible from pure physics standpoint. The atmosphere is there. The drag forces exist. If you could design a vehicle with thermal protection system that could handle the heating, and with structure that could handle the deceleration loads, you could achieve the velocity change through atmospheric interaction. But chances are you could probably only manage partial aerobraking, maybe bleeding off 10 km per second or so due to survival limits before thermal or structural failure occurs, rather than achieving the full 34.7 km deceleration needed, which would reduce the fuel requirements for rocket-based propulsion by roughly a third if you're using plasma drive. If aerobraking provides 10 kWs of the needed 34.7 kWs, then rocket propulsion only needs to provide 24.7 kWs. With 1000 kWs exhaust velocity, mass ratio, E gas 24 7000, 1.025, fuel mass, now 3 billion tons, x 0.05, 75 million tons. That's 30% reduction compared to the 105 million tons needed without aerobraking. Certainly helps, but doesn't fundamentally solve the problem. Still requires enormous propellant expenditure and enormous power generation to run plasma drive. Okay, so now we know the various different methods of propulsion that might be able to pull this off for the full spacecraft, turning around entire 3 billion ton object and sending it back toward Earth. Chemical rockets, impossible. Fuel requirements exceed object's mass by factors of thousands. Ion engines, barely possible. Requires 1/3 of object's mass as propellant. Plasma drive, potentially feasible, requires roughly 100 million tons of propellant, which is within observed mass loss rates from tail activity, but requires power generation of 10 petawatts, which seems impossible. Aerobraking, theoretically possible to achieve full velocity change through atmospheric drag alone, but practically impossible due to thermal and structural loads that would destroy the object, all of them requiring staggering amount of energy or fuel, or requiring survival of conditions that would rip natural asteroids apart. But plasma drive being the most plausible if the power generation problem can be solved. Certainly challenging. Certainly requiring technology beyond what humans currently deploy operationally. But potentially feasible for civilization that's advanced beyond our current level. Now let's consider a different scenario, something less ambitious than turning around entire spacecraft. What if 3i Atlas were not actually trying to execute full reversal? What if this very radical maneuver, decelerating massive object by 34.7 km/s, surviving either the rocket propulsion burns or the atmospheric entry, executing precision gravity assist that sends it back toward Earth? What if that's not actually the mission profile? What if instead it were trying to dispatch a probe of some kind? But let's make it a little bit more ambitious than tiny CubeSat. Let's say it's a 10-ton space platform of some kind, substantial piece of hardware, maybe the size of bus, equipped with instrumentation and communications and power systems and propulsion for maintaining position. Sort of an observational satellite to be deployed into Jupiter's Lagrange points, one of the 2 Lagrange points at the area where 3i Atlas will be passing. What if it were to do something like that instead of trying to turn the entire mothership around? What kind of propulsion, what kind of energy would be necessary to deploy something a lot less ambitious than trying to turn the whole ship around? To insert a 10-ton probe into stable position at one of Jupiter's Lagrange points, where it could loiter indefinitely, observing Jupiter's magnetosphere and moons and rings, keeping the inner solar system under long-term surveillance, establishing permanent presence in the outer solar system that could continue operations long after the mothership departs. All right, so in this probe deployment case, we're not taking advantage of Jupiter's gravitational pull for slingshot maneuver. We're not trying to decelerate into capture orbit and then accelerate back out. We're just trying to insert a probe into a location that essentially matches Jupiter's orbital motion around the Sun, specifically into one of the Lagrange points where Jupiter's gravity and the Sun's gravity create stable equilibrium, allowing objects to maintain fixed position relative to Jupiter without continuous propulsion. The velocity difference between 3i Atlas's current trajectory and the orbital velocity required for Lagrange point station keeping is substantial. The heliocentric speed of 3i Atlas when it reaches Jupiter's distance will be approximately 60.88 km per second. That's accounting for how its velocity decreases as it climbs out of the Sun's gravitational well, converting kinetic energy into gravitational potential energy as it moves farther from the Sun. And the orbital angular velocity of Jupiter, that is to say, not necessarily its simple orbital speed, but the angular speed relative to 3i Atlas's direction of approach, accounting for the geometric configuration and the vector directions, will be approximately 12.21 km per second. This is the velocity that an object needs to have to orbit the Sun at Jupiter's distance, while remaining in fixed position relative to Jupiter, essentially co-orbiting with the planet. Meaning you have to take the difference of those two figures, 60.88 minus 12.21 equals 48.67 km per second. That's the velocity change required. That's very fast. Faster than the 34.7 kilometers we calculated for the mothership deceleration because the probe is moving with 3i Atlas's velocity and needs to slow down enough to match Jupiter's orbital speed, rather than just slowing to twice Jupiter's orbital speed for gravity assist, and also a 10-ton object. We're still going to be looking at quite a lot of energy here despite the relatively small mass compared to the billions of tons of the mothership. But I think 3i Atlas would be better off avoiding putting an onboard propulsion system, at least not a big one, on this orbital platform. Carrying chemical rockets or ion drives or plasma drives on the probe adds mass for engines and fuel and power systems, mass that could instead be dedicated to scientific instruments or communications equipment, or whatever the probe's actual mission systems are. Instead, why not use propulsion system that requires no propellant whatsoever on the probe itself, where all the propulsion infrastructure remains on the mothership, and the probe is pushed or pulled into position using external forces. This is a concept called beamed propulsion, and several variants exist depending on what you're beaming and what you're pushing against. The simplest version conceptually is a laser sail, also called light sail or photon sail. The idea is to put a large reflective solar sail onto the probe platform and then use high-energy laser mounted on the mothership, providing the necessary photon pressure to decelerate the object. Photons carry momentum even though they're massless, and when they reflect off a surface they transfer twice their momentum to that surface, once when absorbed and once when re-emitted in opposite direction. Solar sails work on this principle using sunlight, but sunlight intensity decreases with square of distance from the Sun, making solar sails inefficient in outer solar system. At Jupiter's distance, solar radiation is about 27 times weaker than at Earth's orbit. Not enough to provide rapid acceleration or deceleration, but laser from mothership can be as intense as you want it to be, depending on power available, and intensity doesn't decrease with square of distance if the laser beam is well collimated, if the beam's spreading is minimized through proper optical design. Here's the problem with laser sails, though. High-energy laser means very high-energy photons that don't have a whole lot of stopping power despite their energy. Photons travel at the speed of light by definition, 300,000 kilometers per second. They're moving so fast that each individual photon-sail interaction transfers only a tiny amount of momentum. The momentum of a photon equals its energy divided by the speed of light, P terces E kc. So for given energy input, photons provide much less momentum transfer than slower moving particles would. That's why solar sails have to be so enormous in area, square kilometers of ultra-thin reflective material, absorbing as much solar energy as possible in order to get enough cumulative photon momentum transfer to produce even modest acceleration. The acceleration of a light sail is proportional to the power incident on the sail divided by the mass and divided by the speed of light. With power P, mass m, and speed of light c, the acceleration is a Kernzund p mxc. For our 10-ton probe, which is 10 per 4 kilograms, if we want to achieve velocity change of 48.67 kilometers per second in time period of let's say 1 month, which is approximately 2.6 million seconds, the required acceleration is a bisschen 48,670 cm, 2.6 x 10^6, 0.087 mern s2. You need perhaps 200 gigawatts of electrical power generation on the mothership. That's already enormous, 20 times the electrical output of largest power plant on Earth. But wait, It's worse. The calculation assumes perfect conversion of a laser energy into momentum, which doesn't happen. The actual momentum transfer efficiency depends on sail reflectivity, and on absorption losses and on beam quality. Real systems might achieve 50% efficiency, so double the power requirement, 400 gigawatts electrical, 112 gigawatts laser output, and the total energy required over 1 month of beaming, 112 gigawatts times 2.6 million seconds equals 2.9 × 10 to 14 watt-seconds, which is 2.9 second ds per 14 joules. That's 290 trillion joules, or 290 terajoules. Actually, let me recalculate that more carefully. 112 pesks 10 or 9 watts times 2.6 squen 6 seconds equals 2.9 squen 17 joules. That's 290 petajoules, or 290 cant dab 15 joules. To put this in context, that's the energy equivalent of roughly 15 megatons of TNT. That's a large thermonuclear weapon. That's the explosive yield of the Castle Bravo test, the most powerful nuclear weapon the United States ever detonated, and we're saying you need to convert that much energy into coherent laser light and beam it at a sail over the course of a month to slow down a 10-ton probe by 48.67 kilometers per second. That doesn't seem very efficient at all. Is there some other way to decelerate this object without having to use such an insane amount of energy? Without requiring energy equivalent to nuclear weapon just to slow down bus-sized probe? There must be better approach using particles that have more momentum per unit energy than photons do. And indeed there is. There's another concept called a magbeam, magnetic beam propulsion. This was developed and analysed by Robert Wingley at the University of Washington and was funded by NASA's Institute for Advanced Concepts in the early 2000s as potentially viable approach for interstellar precursor missions. The concept is still theoretical, but the physics is well understood, and nothing about it violates known physical laws. What would happen is 3I Atlas would generate a high-powered collimated beam of ionized plasma, essentially an artificial magnetic field structure propagating through space, and this beam interacts with a magnetic sail deployed from the probe. A mag sail is just a large superconducting loop that generates magnetic field. The magnetic field creates what's called a mini-magnetosphere around the probe, a bubble of magnetic field that repels or deflects incoming charged particles. Normally a mag sail would interact with the magnetic field of a star, with the solar wind, the stream of charged particles flowing outward from the sun, in order to speed up or slow down. You orient the sail so the solar wind pushes you in the direction you want to go, providing propulsion without expelling propellant. But the magnetic field of the sun and the solar wind density are far too weak at Jupiter's distance for this kind of system to work efficiently. At 5 AU from the sun, solar wind density is about 25 times lower than at Earth's orbit, and the momentum flux is correspondingly reduced. So instead of relying on natural solar wind, you would generate an artificial magnetic field, a beam of ionized plasma expelled from the mothership at controlled velocity and with controlled density. The mag sail on the probe creates a mini-magnetosphere that repels or deflects the incoming plasma ions in similar way that Earth's magnetic field protects us from the solar wind, from cosmic rays, from charged particle bombardment. The deflection transfers momentum from the plasma beam to the sail, providing thrust. This approach would actually be far more efficient than a laser sail because the particles used to propel a mag sail are much, much larger compared to photons. Plasma ions, ionized hydrogen atoms for instance, have mass. A proton masses about 1.6 10 on 27 kilograms. That's tiny in absolute terms, but compared to photons which are massless, it's infinitely larger in the sense that the momentum to energy ratio is much more favorable. That's about 15,000 times better momentum to energy ratio than photons, meaning for same momentum transfer, you need 15,000 times less energy if you use plasma particles at 40 km/s instead of photons. That's enormous efficiency advantage. That's the difference between requiring nuclear weapon energy equivalent and requiring something that's actually achievable with plausible power systems. That's 12,200 kilograms of plasma, about 12 tons. That's very manageable. That's mass comparable to the probe itself, and it doesn't all need to be expelled at once. It can be expelled continuously over the deceleration period. Compare that to the 73,000 terajoules required for laser sail. The mag beam requires about 7,500 times less energy. That's the efficiency advantage from using massive particles instead of photons. Suddenly, the energy requirements drop from equivalent to thermonuclear weapon to equivalent to few thousand tons of TNT, or comparable to large power plant running for a few hours. Based on this design concept, a 300 megawatt thruster system based on 3i Atlas, and keep in mind, the thruster doesn't have to be on the platform itself, it's on the mothership beaming plasma toward the probe, could achieve the required momentum transfer in only 9 to 14 hours of continuous beaming if operating at full power. Let me verify that. Power, energy, time. If energy is 9.7 to 610 to 12 joules and power is 300 kW 6 watts, then time 9.610 to 12. 3 to you are 8. 3.25 life 4 seconds. That's about 9 hours. Yes, that matches the estimate. Alternatively, if you did this over the course of an entire month in order to provide more gentle deceleration, to avoid stressing the probe with sudden velocity changes, to allow more precise trajectory control, to spread the operation over longer time period reducing peak power requirements, the average power requirement drops to 9.610 joules, 2.6 seconds, 3.6 watts. That's 3.75 megawatts average power. Comparable to a few wind turbines or a small coal power plant or a modest solar farm. Definitely within the capability of an advanced civilization. Even within the capability of human technology, if we were trying to accomplish this with current engineering. Not trivial. 3.75 megawatts sustained for a month is substantial energy expenditure, but not requiring exotic physics or unobtainable power sources. So deploying a 10-ton probe into Jupiter Lagrange point is actually quite feasible, using mag-beam propulsion, much more feasible than trying to turn around the entire mothership, requires manageable energy, requires manageable mass of propellant, requires technology that we understand and that's being actively researched for future space missions. But could we possibly use the same sort of setup to decelerate 3i Atlas itself, to decelerate the entire multi-billion-ton mothership instead of just a small probe? Well, perhaps, but you'd need a very, very large mag sail to decelerate something that massive. The momentum that needs to be transferred scales with the mass. For 3 billion-ton object requiring 34.7 km/s velocity change, the momentum change, and that mag sail would need to interact with something to push against. In the probe scenario, the mag sail interacts with the artificial plasma beam from the mothership. But what would the mothership's mag sail interact with? It could potentially interact with the Sun's magnetic field and solar wind, but as we noted, those are very weak at Jupiter's distance. How could that possibly work? How could you get meaningful deceleration from interacting with weak solar wind at 5 AU? Well, why not use the anti-tail? This is where we start connecting the unusual observations of 3i Atlas to potential propulsion mechanisms that might explain those observations. The anti-tail that we've been puzzling over, the 400,000 kilometre structure pointing toward the Sun that defies normal cometary physics. What if it's not just gas and dust being expelled randomly? What if it's a functional structure? As near as we can tell from spectroscopic observations, the anti-tail is comprised of ionized material, plasma, not neutral gas, high-energy ions that are electromagnetically active rather than being inert dust particles. If you inject more plasma into the anti-tail, if you continuously feed it with ionized material from the surface or from sublimating ices that are deliberately ionized, and if you inject this plasma into a ship-generated magnetic field that shapes and controls the plasma distribution, you could inflate a massive mini-magnetosphere. This bubble would expand electromagnetically, not mechanically. You're not building physical structure that extends hundreds of thousands of kilometers. You're creating magnetic field structure that organizes the plasma into extended configuration. The magnetic field deflects incoming solar wind over a huge area without needing mechanical supports or solid materials. It's all electromagnetic, fields and plasma interacting according to magnetohydrodynamic principles. Now, if you're trying to decelerate enough to achieve about 48 kilometers per second deceleration for Lagrange point insertion, that's not going to happen even with something as enormous as the anti-tail. Even if it were 1,000,000 kilometers in radius rather than 400,000 kilometers, even if the solar wind was stronger, you'd still only achieve a few kilometers per second of deceleration over reasonable time periods. But wait, actually, If you sustain this over a couple of years, you might accumulate significant velocity change. 2 years is about 6.3 7 seconds. Deceleration of 0.866 km per month times 24 months equals about 20.8 km total. That's substantial. That's approaching half of the required deceleration for the mothership turnaround scenario. So you could at least employ the anti-tail, again, assuming the anti-tail is a giant artificial magnetic field structure rather than being passive cometary emission, to provide at least some deceleration without any propellant being required beyond the plasma needed to inflate and maintain the magnetic field structure. The energy cost is just the ionization energy for the plasma, plus the energy to maintain the magnetic field, which is much less than the kinetic energy of expelled propellant in rocket scenario. You could combine this with other solutions in a multi-stage deceleration profile. The magnetic field provides continuous gentle deceleration of maybe 1 km per second per month, sustained over a year or two as you approach Jupiter. That gets you perhaps 12 to 24 seconds of the needed 34.7 kmph. Use some aerobraking during Jupiter approach to bleed off another 10 kmph, accepting the thermal and structural stress but designing for it with advanced materials and active cooling. And then employ plasma drive for the final few kilometers per second of deceleration that brings you to the precise velocity needed for gravity assist. Complicated? Absolutely. Requiring coordination of multiple propulsion systems operating sequentially and simultaneously? Yes. Requiring advanced engineering and precise trajectory control? Definitely. But impossible? No. Actually feasible if you're willing to accept the complexity and if you have the technology to implement mag-sail structures and plasma drives and thermal protection systems at the required scales. But then again, given what we have observed with this object, this massive anti-tail structure that seems to defy the solar wind pressure that should disperse it, that maintains coherent beam-like collimation across hundreds of thousands of kilometers when natural gas dynamics predict rapid expansion and randomization, it actually is visual representation of giant mag-sail if you interpret it that way.